Hello. Today we are going to discuss interval estimation, one important subject in inferential statistics. Inferential statistics is the core content of statistical analysis. Inferential statistics basically use the sample information to estimate or test about the population information. Throughout this discussion, we are going to use population means as a way to illustrate how to conduct inferential statistics, but the same set of techniques can be applied to many other population parameters, such as population variance, population standard deviation, and population correlation coefficient, so on and so forth. So the techniques are pretty general and very applicable to many other circumstances. We just use the population mean as a relatively easy way to illustrate the techniques. There are two types of inferential statistical techniques: making estimation and inference about the population mean by using a sample mean. Also, we can conduct hypothesis testing regarding the value of a population mean by using a sample mean. Today, we're going to discuss interval estimation, and next time we discuss hypothesis testing. Interval estimation of the population mean. Let's first talk a little bit about the point estimation. So-called the point estimation is use one point. For example, use a sample mean to estimate the population mean. Here we just got there to collect the sample and calculate the sample means, and if the sample is taken properly to make it representative of the entire population, this sample mean may be quite close to the true population mean. Now, what the standard we use to gauge whether we have an appropriate estimate of the population mean? We use a standard so-called the unbiased estimate. An unbiased estimate means that if you take many samples and calculate the sample means, eventually if all the sample means of the same size generate a mean of sample means that is equal to the true population mean, we call this way of estimation is unbiased, and the result is called unbiased estimate. So the unbiased estimate really tells us a standard we use to evaluate whether we have appropriate method of doing estimation. And in the same way, an unbiased estimate of population standard deviation would be a kind of a method that after you take many samples and calculate some sort of estimate of population standard deviations, the mean of all the sample standard deviations is equal to the true population standard deviation. If that happened, we'll call this estimate an unbiased estimate of the population standard deviation. Based upon the unbiased estimate criteria, let's just look at for the population mean and population standard deviation. What are the unbiased method, or what we call unbiased estimator? Let's look at the unbiased estimators for population mean and the population standard deviation respectively. For the population mean, the unbiased estimator is the sample mean. And the sample mean, we know, can be calculated by using this formula. And this formula actually is the same as the formula of calculating population mean. All the cases find the sum and divided by the number of cases. So this formula gives us the unbiased estimator of the population mean. So the sample mean is the unbiased estimator of the population mean. What about the population standard deviation? When we study descriptive statistics, we introduce the formula for sample standard deviation. At that point, we emphasize that this formula looks different from the formula we use to calculate population standard deviation. Remember, the formula we use to calculate the population standard deviation is the sum on the top in this formula over all the terms divided by the number of cases, n. So that is the formula for population standard deviation. At that point, when we introduce the formula for sample standard deviation, we emphasize that at the bottom we do not use the number of cases. Instead, we use the number of cases minus 1. At that point, when we introduce this formula the first time, we did not really explain why we use n minus 1. We only said that we explain this later. Now, this is the time we explain why we use this formula, because this formula gives us the unbiased estimator of the population standard deviation. If we do not use this formula, if in this formula we use n at bottom instead of n minus 1, that would give a biased estimator of the population deviation. If you use the formula at the bottom with n and calculate all the sample standard deviations, eventually if you calculate the means of all the sample standard deviation from the formula with n at the bottom, that result, the means of all the sample standard deviation, will be smaller than the true population standard deviation. So if you use a estimator with n at the bottom, it give a result that underestimate the true population standard deviation. That's why for unbiased estimator of the population standard deviation, we actually use this formula with n minus 1 at the bottom as a correction. Okay, we call this n minus 1 a degree of freedom, n minus 1. Okay, so that's the reason why when we come to calculate sample standard deviation, we use this formula with n minus 1 as denominator, not n. Okay, so this is the concept of unbiased estimator for the point estimation. But the point estimation has some limitations. One important limitation for the point estimation is that there's no measure of precision to the estimation. You don't really get an idea of how precise, how close a sample mean is to the true population mean. You know, you just got there to collect a sample and calculate the sample mean. After you calculate the sample mean, you really have very little to say about how close this sample mean to the true population mean. And that is what brings about the issue of interval estimation. Interval estimation is to use two numbers to establish an interval around a sample mean. Then we use this interval to enclose the true population mean. And with this interval, we would have a sense of certainty or confidence that is expressed by a probability. For example, we can say that we are 95% confident that this interval encloses the true population mean. Or if we want to be more confident, we can build a 99% confidence interval. And so that would really give a sense of precision, and also by increasing the sample size, we can also change the width of the interval to change the accuracy of the estimation. So for these reasons, interval estimation has some advantage over the point estimation. So today we're going to discuss interval estimation using the population mean as a example to illustrate the techniques. Okay. Now, before we get into the actual content of interval estimation, I'd like to briefly review two subjects that we have learned from the past material. First, let's briefly review the central limit theorem. We know the central limit theorem explains the relationship between the population distribution on the one hand and the theoretical sampling distribution of the sample mean on the other hand. Okay, specifically, we know that the means of the population is equal to the means of the theoretical sampling distribution of the sample mean. In addition, the population standard deviation divided by the square root of sample size equals standard error, which is the standard deviation of the theoretical sampling distribution of the sample mean. So this is what we learned from the central limit theorem. Second subject I'd like to review is about the characteristics of normal probability distribution. I use the theoretical sampling distribution of the sample mean as a way to illustrate the characteristics of normal distribution, mainly concerning the percentage distribution of cases along the distribution. Here is the mean in the middle. We know as a normal distribution, it conforms to these empirical values, that is around the mean, both sides of the mean, one standard error below the mean and one standard error above the mean, you have 68.26% of all cases. In this case, since the distribution is formed by all the sample means of a certain size, you know that within this bound, one standard error below and above the mean, you have 68.26% of all sample means of a certain size. Then, within this interval, the lower bound is 2 standard error below the mean. The upper bound is 2 standard error above the mean. Within this interval, you have 95.44% of all sample means. So 2 standard error below the mean and 2 standard error above the mean, you have 95.44% of all sample means of a certain size. In addition, 3 standard error below the mean, 3 standard error above the mean. Within this large interval, you have 99.75% 4% of all sample means of a certain size. Now we are ready to go to discuss interval estimation technique.